This is one of the three Anil Kumars that we have. As I think probably we never had three at any one point of time. So we always had two. So that is as far as I know. But so Anil Kumar was very much part of our department, and so I will go through basically briefly his background. So Professor Anil Kumar, of course, did his PhD. So he goes back a long time in his association with our department. PhD from this very department, well, located in the so-called old building, with Professor E.S. Rajgopal, and subsequently, that was in 1979, and subsequently he spent time as postdoc, first in University of Pittsburgh and then in University of California, Santa Clara, and then sorry, but it says Santa Clara here. I don't know how did that get changed. Probably the same thing is printed on the poster, so we should correct it. Um, so and then he joined the department as a faculty in 1987, and he remained a faculty till 2002, before an untimely and unfortunate demise. For some of you who probably are not aware, this footbridge that you see basically spanning the Gymkhana and this side of the campus, I think was made precisely for this reason. It's very unfortunate, but I mean, if you take such things to have a safer way of going between two parts of the campus, then I don't know what to say. But anyway, that's what it is. So uh, Anil Kumar, of course, is well known for his work on phase transitions and critical phenomena. And he has worked on all sorts of systems, solids, uh, liquids. I mean, multi-component liquids, and so on and so forth. And so it was quite. He is quite well known in these uh, areas, using a variety of measurement techniques to study this light scattering turbidity, but also electrical conductivity, AC, and DC electrical conductivity, resistivity. So with this few words about Professor Anil Kumar, I will not now, before I ask Abhishek to come on stage and deliver the lecture today, just a few words of introduction. Probably most of you know him, but nevertheless. So Abhishek, of course, is well known to us. Um, a brief background. So his PhD from TIFR Mumbai, and subsequently he actually spent some time in IISc, IISc and RRI, and then of course he joined RRI as a faculty, where he remained till I guess about 2011 or 2012, before he moved to ICTS in 2012, and he has been there ever since. So I mean, Abhishek, has made valuable contributions in the area of statistical physics, condensed matter physics, and the interface of these two, and he is kind of widely recognized for his contributions through various awards. I will not go listing, but just to name a few, the Swarna Jayanti and the Bhatnagar Award, the ICTS Prize and the Birla Science Prize, and he's also fellow of the three Science Academies of India. So I think with this brief word of introduction, I request Abhishek to deliver the Anil Kumar Memorial Lecture. Abhishek.
Okay. 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 Yeah, thanks, Jaydeep, for the kind introduction. And first, I'm really grateful to Shumilon and the other organizers for the invitation to this symposium and to give this. So I'm really honored to give this lecture in the memory of Professor Anil Kumar, with whom I have some very brief interaction. So I was a postdoc here from '98 till 2000. Yeah, so I have a long association with IISc. I think the first time I came was 33 years back. I was working with Sriram as a student, like I was a master's student then. Okay, so yeah, so it's really special always to be at IISc. Okay, so today I'll talk about this problem. About the connections between microscopics and hydrodynamics. So, so this is just this work is done with a lot of people have been working on this problem for some time since 21. So this is Shubhadeep Chakraborty, a former postdoc who's now at this place, and these two are two former students, Santosh Kannappa and Sahil Kumar Singh. This is Paul Krapivsky from Boston. So most of what I'll talk about is this work, and there's some more recent work on with these colleagues, which I will not talk about. Okay, so the main idea of the talk is so there are two descriptions of matter. One is just the microscopic description, which is Newton's equation of motion for the number. So let's say if I want to describe this room, I can look at all the molecules and look at all the write Newton's equations for them. That's the microscopic description. And then there's a macroscopic description, which is a kind of coarse-grained view where I don't look at my details, but at coarse-grained observables. And here one can talk about two classes of systems, like systems which are in equilibrium, and then one talks of thermodynamics, statistical mechanics, and so on. And then there are systems that are not in equilibrium, where one talks about hydrodynamics and non-equilibrium statistical mechanics. And basically, what I will talk about is like how, and they're describing the same system, how, I mean, well, do these two descriptions agree? Okay, so please feel free to ask questions at any point. Uh, okay, so let me start with some more details. So the microscopic laws is like if I look at the room in the gas in this room, it's composed of large number of molecules, and I need to specify all their positions and momenta. And then there is Newton's equations, which tells me how this system evolves, right? Or equivalently, it's this is Hamiltonian dynamics. So there's some Hamiltonian function which basically tells me everything at a microscopic level. Okay, so I'll stick to classical description, though one can do everything also for quantum systems. Okay, and then if I'm looking at equilibrium systems, there's the macroscopic laws are basically thermodynamics. So at a macroscopic level, for example, in this room, what I can really measure are things like pressure. I can put a pressure gauge and measure the pressure in this gas in this room. And then I can measure the temperature and density. These are the things which I can really measure. Okay, so they are sort of coarse-grained variables. Then there's this classical theory of thermodynamics, the first law of thermodynamics, second law of thermodynamics, which tells me how these things are related. And then yeah, so there's this equations of state, and then I can measure like interesting physical observables are things like specific heat, compressibility, and so on. Okay, so this is like from thermodynamics, one can extract a lot of information. And in particular, there's this amazing function called entropy, which is introduced in thermodynamics. Okay, so okay, then one can understand thermodynamics using equilibrium statistical physics. And here, basically, we have this theory of Boltzmann and Gibbs. And the basic idea is that that to describe like most observable properties, I don't need all the details. I need just a description in terms of what are the conserved quantities of the microscopic model. Okay, and these are typically, for a typical system, the conserved quantities are the total number of particles, the total energy, and the total momentum. The total momentum is usually not relevant when I talk of systems in equilibrium. I can work in a frame where total momentum is set to 0. So then just total number of particles and total energy are relevant. And then what equilibrium statistical physics tells us is that we compute this kind of, we count the number of states with a given energy, or find the phase space volume corresponding to some fixed energy. And from this, taking the log of this, this is Boltzmann's famous formula, gives us this entropy, which is now a function of just very few variables, right? And then this is quite amazingly, or I mean, from this function we can obtain all properties, all equilibrium properties of the system. Okay, so equations of state space, everything is contained in this single function. Okay, so I mean, so if you really think about it, it's quite magical. I mean, that I mean, you can have such a simple description for a very complicated system. Okay, so so far this is equilibrium, and now let's talk of systems which are not in equilibrium. So, for example, the gas in this room. I mean, if there's no one sitting here, then and it's completely closed, then it's a system in equilibrium. But right now, it's not obviously not in equilibrium. There are temperature gradients, there are flows everywhere. So these are examples of systems out of equilibrium. And then a good description of such systems is to use the idea of local equilibrium. So basically what we say is that in this room, if I put a thermometer at one point, I get some temperature, but if I move it, there's some temperature, like I'll measure different temperatures everywhere, right? So if I take a small box, if I take a very tiny box, then within this box, it's kind of in equilibrium. Okay, so there's a well-specified pressure, temperature, and density. And then this, of course, is different at different places. Okay, so this is the idea of local equilibrium. Uh, and yeah, so basically you divide the entire system into large number of small cells, but each of these cells still contains large number of molecules, right? Yeah, so the fact that we have large numbers is really important, and it gives rise to this why the statistical description works so well. And so a good description of each cell is just by looking at the conserved quantities. Okay, so particle number, momentum, and energy in that in each cell. And then of course things are changing with time, and hydrodynamics tells us how the different cells interact. Okay, so again, to be more specific, this is the local equilibrium description. So let's say I have a pipe and there's water or some gas in it, and these are the molecules. Then in what I do is I consider this small cell of size L, and then just count the number of particles, the total momentum, and the total energy in this cell. And from this I can construct these fields, right? I can construct the density field, momentum field, and energy density field. So I'm just so one can do this in any dimension, but I'm just thinking of a one-dimensional system. Okay, so there are these three fields corresponding to the three conserved quantities. Okay, so that's crucial. I should only look at conserved quantities to tell me what are the important hydrodynamic variables. Okay, so now so these are functions of both position and time. And okay, so I can either look at this density, momentum, and energy density, or equivalently, I mean, the momentum is kind of density times velocity. So I can define a velocity field which is more physical, and then I can define a temperature field from the energy density. Okay, so these are like really the physical fields which are easy to measure in an experiment. And okay, and because they correspond to conserved quantities, they evolve very slowly, and that's why they are given by hydrodynamic equations. Okay, so each of these fields satisfy some kind of a continuity equation. Okay, so now let's see what are the equations by which these fields evolve. Okay, so these are the equations of motion for the hydrodynamic fields, which now replace the Newton's equations at this macroscopic description. Okay, so the equations of so these equations can actually be written without caring about them. Were written without caring about the microscopic description. Okay, so when Euler and Navier-Stokes they wrote these equations, I mean, the microscopic picture in terms of atoms and so on were not really so well established. So they wrote these equations just pure from just intuition and physical, yeah, just physical intuition. Okay, so these are three equations for the three conserved quantities. I'm doing one dimension, so there's only one momentum field. Okay, so this is the momentum field, this is the density field, and this is the energy density field. Okay, so this is the structure of the equations. They all look like del rho del t plus some divergence of some current equal to 0. So that's the and then the current has basically all these terms. Okay, so this is okay. So now one thing you notice is that I've written these red terms and then these black terms. Okay, so the black terms are so these are currents rho v square plus p. So this is a current which depends on the fields. Okay, and while these currents depend on gradients. Okay, so these are what are known as dissipative terms or Navier-Stokes Fourier term, and the remaining part are what I'll call Euler terms. Okay, so Euler wrote this set of equations without the red terms, and Navier-Stokes basically wrote this term with eta. Eta is just the viscosity of a fluid, and then Fourier comes in where you add a thermal conductivity term. Okay, so yeah. Yeah, I'm here writing one dimension. Yeah, yeah, yeah. P is the pressure. Is here it's just the pressure. Yeah, in higher dimension it would be the pressure tensor, but in 1D, I mean, just for simplicity, I'm writing 1D equations. Yeah. Any other questions?
No, but at this level of a description for a fluid, P would still just be a scalar.
Yeah. Here.
Your pressure tensor, your stress tensor will only go into the viscous terms. I mean, it's just a simple fluid.
Yeah, if it's a simple fluid, it would still be this, right? Yeah. I would have a divergence of P delta Ij, right? Yeah. Yeah, right. Yeah. Okay, so yeah, but I'm just writing 1D equations for the moment. Okay, so so in this equation, there are three. So these are three partial differential equations for these three fields, and so okay, so this is Euler plus dissipative is what is Navier-Stokes Fourier. So Navier-Stokes are this eta term which corresponds to viscosity, and Fourier is this term. Okay, and then in this equation you see the pressure. But the pressure is something which depends on the density and temperature just from equilibrium physics. So it's not an independent field. So it's also known. And then there's this epsilon, which is the energy per particle, which has a component which is because the fluid is flowing. So that's just mv square by 2. And then this is the internal energy. Okay, and the internal energy is again something we know from equilibrium physics. Okay, so I mean from this you can see that it's a closed set of equations for these three fields. Okay, and then okay, so this is some. So the connection to microscopics of this at this level can already be seen that these things can be obtained from equilibrium statistical physics, just from that entropy function, the energy, the internal energy, and the pressure, and then there are these transport coefficients, which is the viscosity and the thermal conductivity. Yeah.
Is there any context known where people have found that the equation of state, I mean the U of rho t and P of rho t,
Yeah.
changes because of the flow?
Uh,
The equilibrium equations are not adequate. Is there any context?
I at least I don't know. Like you're saying, because of the flow, it says yeah. No,
Equilibrium is a constant,
right. Yeah.
but there must be some deviations from it in principle if the flow is.
Yeah. I mean, right. Yeah.
It still remains macroscopic, but you have to change the equation. Is there any such?
At least I don't know, like of a very clear example. I'm sure it's there, but I don't know. I don't know if Sriram knows.
I mean, a half-baked answer is that even if you look at the pressure, there is that P, but in principle, the thing that's acting like a pressure has the rho v squared also in it. So I mean, but the only thing
Yeah,
is that
that's
it's the idea still is that you have a piece that comes from thermodynamics, and then other things are given to you by the equation.
yeah.
And there's a certain sense in which this is, there isn't room for the particular thing you're talking about in this context with low weight.
Right. Yeah. Yeah. This is within. Yeah, okay. Okay, so this transport coefficients are something also you can calculate from equilibrium physics using something called linear response theory and Green-Kubo formulas. Okay. So that's where the all the information about the microscopics has gone. Okay, so okay, I just want to point out this very nice quotes from this book by David Tong. So this, I mean, David Tong, of course, like many of you know, he writes things very nicely. And he has this, in the introduction chapter, he has this comment, I mean, take anything in the universe, throw a bunch of it in a box and turn up the heat. Then it doesn't matter what you started with. The motion of this substance will be governed by the equations of fluid dynamics. Okay, so this is a remarkable statement. There are a lot of different things in the universe, and we go to great lengths to understand their properties. Yet, if you heat them, most of the differences disappear. When things get hot, everything looks the same. Okay, so it's quite amazing. Like, it doesn't depend on the details of the gas. I mean, it could be quark-gluon plasma. It could be, I mean, what not. But finally, they have the same simple equations, and there are a few quantities which, like conductivity and so on, which determine things. Okay, so I think it's quite amazing, and this amazing universality comes because basically the equations of fluid dynamics are based on the laws of conservation of mass, momentum, energy, and these are of course universal. And also at play is the law of large numbers. Okay, because I mean, so whenever you have large numbers, there's some averaging which happens, and details go away. Okay, so I think that's, yeah.
The change of density actually phase transition may take place, right? As you are mentioning quantum plasma
Yeah.
also, but as in the interference, as well discussing.
Right,
So
yeah.
it may happen that initially, I'm just thinking in terms of a particular point of view, initially the nuclear matter, that's very high density density.
Yeah.
And then nuclear matter could be quark matter.
Yeah. Right,
So
yeah.
phase transition may take place. In that sense, equation of state could have been changed.
Yeah, so I mean, you can write, of course. I mean, so the equation of state contains that has that information, right? With which, right? Yeah. For example, if you use the van der Waals equation, in some sense, it has that information of phase transition. So, yeah. So that equation. But you still, it's
Parameters and all, you may have to add additional fields.
yeah. Then of course you'll have completely right. Yeah.
But it's in the same lane. Also, why do you have to keep things
Yeah, this is what he says, and yeah, I also had the problem. You don't, like, you can have a cold at very low temperatures. You can have a gas which is described by hydrodynamics.
If it has a temperature.
Yeah, if it is, I mean, yeah, I mean, I can go on. Okay, so now the main question that we want to ask, yeah, you can ask once in a while questions, but too many questions. Okay, so I mean, okay, so now the main question we want to ask. Okay, first question is there a rigorous? I mean, the same system is described by these two pictures. Is there a rigorous derivation of hydrodynamics from Newton's equation? So this is actually kind of part of Hilbert's sixth problem, and so far it's unsolved. There's a very nice review by this Isabel Gallagher. It's called From Newton to Navier-Stokes. Uh, okay, so I mean, there's been, of course, a lot of progress. One kind of systematic way of doing it is you start from Newton's equation, then you can derive Boltzmann kinetic theory. You can't derive means you can, in some approximation, that's part of this Chapman-Enskog theory. And from Boltzmann kinetic theory, you can get to hydrodynamics again with some approximations. Okay, so this is one way to kind of derive hydrodynamics, but it's still a very open problem, at least from a mathematics point of view. Okay, but anyway, what we want to see is like how actually, if you just, can we test how accurate is this hydrodynamic description and what are the limits of its applicability? I mean, you might imagine that if it's very low density or there's some sharp discontinuity and all, it might break down, right? So yeah, that is maybe what is HRK's question. Like in some extreme situation, maybe this assumption of local equilibrium breaks down. So are there, I mean, so this is what we want to test. I mean, surprisingly, there are not too many accurate numerical comparisons, and this is, we'll consider this blast and splash problems and try to understand this. Okay. So let me talk now about, explain what these problems are, blast and splash. Okay, so here is a video. So, so what I'll show you is like it's a two-dimensional system, and there are initially there are 10 to the power 5 hard disks placed in equilibrium. They're all at rest. Okay, and then I at the center of this system I excite a few particles and then see what happens. Okay. Okay, hopefully this will work. Okay, yeah. Okay, so here you can't see, but there are like this number of hard disks which are initially uniformly distributed, and they are all at rest. Okay, and then at the center, just 4 particles are excited with total momentum 0 and with some fixed energy. Okay, some finite energy. And then you observe like so then each particle excites some other particle, and then so you have a evolving front, right? So you see this front growing. Sorry. Yeah, so this red is all the excited particles which have no. So initially everyone at rest. Yeah, anyone with a, so afterwards everyone is moving now, right? So this initial energy has gone into all these particles on this radius. So okay, so the main things we observe is that there's a very sharp front. Okay, and it's a, so this is there's a, what is known as a shock in fluid dynamics. Yeah, color is just excited particles, non-excited particles. Yeah, but I didn't say like what is the temperature distribution and all. I'm just saying these are excited particles which are moving now. Initially, everyone was at rest. Now these guys are all moving, right? Okay, so what we'll try to understand is now can we describe this evolving blast using hydrodynamics? Okay, so here what you can see, for example, is like initially it was all uniform density, like the density was uniform. Now there are very few particles at the center. So there's some density distribution. There will be some velocity distribution, and there will be some temperature distribution, right? So we want to understand how these things evolve. Okay. I mean, naively, first thing you would do is maybe there's heat, a lot of heat. Maybe I should just apply heat, the heat conduction equation, and see how to evolve. Okay. Then you would say it should spread diffusively. There should be no front and all. Okay. But what you observe is that there's a nice shock front, and it's okay. It's quite non-trivial. So this is what we want to understand. Yeah.